going to start the course Advanced Reaction Engineering. So, today we will discuss about the effect of pressure drops in packed bed reactor. So, already we have discussed in our previous class regarding this. So, what is called packed bed reactors, and if there is any pressure drops, so how to deal with that. So, today we will discuss about the analytical solutions or the differential equations that we have already derived for the packed bed reactors by considering the design equations of a packed bed reactors. If you look into that, so here these are the two equations we have derived from the design equations of the packed bed reactor. So, the first one, these equations we have derived, that is the dx by dw, that is as a function of pressure as well as conversions of that particular reactions. From the design equations we have derived this for packed bed reactor. And the second equation, so that one was the dy by dw, y is the pressure ratio for the packed bed reactor. So, that is as a function of temperature as well as conversion of the system or packed bed reactor. So, now these two equations if we solve, so then we can see that once there is a packed bed reactor, if there is at the beginning, let us say if there is no catalyst, so then of course there would be no pressure drops inside of the reactor. So, when reactants will pass from the inlet to the reactor to outlet. So, if we placed some amount of the catalyst, some pressure drop would be there with the reactions, at the same time temperature pressures effect would be there. So, here today these are the two equations we have solved. So, let us say for a reactions, if there is means these are the two equations we have derived. So, this is the pressure equation. So, as a pressure as a function of catalyst weight dy by dw. So, as a function of temperature and the conversions also. So, here if any reactions, if we look into any stoichiometry of the reactions, there may be possibility of changes of moles, means initially if we take let us say 2 moles or 1 moles of reactants, and once the reactions is over, then there is possibility of changes of moles in the reactions or may not be. So, two cases may possibility is there, either it is there is no changes of volume or mole changes in the reactions, or maybe there is changes possibilities there. So, if we consider that if there is no changes of moles, means if we take initially 1 moles and after reaction, so 1 moles of product formation is there. So, then there is no fractional changes of volumes due to the reactions. So, in that case E equals to 0 or epsilon equals to 0 we can consider. And also another thing, so if we consider the reactions is operating inside of the reactor at isothermal conditions. So, the temperature of the bed anywhere inside of the reactor is same in everywhere. So, that we consider. So, then from the design equations, that design equations we have this design equation that we have derived. So, if it is isothermal condition T equal to T naught, so then see here we can put T equals to T naught equals to 0 1. So, then that equations would be here, okay, and put E equals to 0, epsilon also 0. So, if we put E equal to 0 and T equals to T naught, so then this part would be become 1. So, these equations will become the differential equation dy by dw equals to minus alpha 2 by y. So, here y is the pressure ratio. So, that we have discussed. So, if this is the packed bed reactors, so here this is P 0 initial pressures, and anywhere pressure if it is P. So, the ratio we are expressing P by P naught, that already you have discussed. So, here it is this. Okay. So, y equals to P by P naught, that is the pressure ratio. So, that pressure is means will change according to the if we go down the length of the reactors with increasing catalyst weight. Okay. So, now if we rearrange these equations we will get these equations. So, now if we put y inside of the derivatives, 2 y was there, that is the outside. If we put 2 y inside of the derivatives, though then that equations would be converted this, and after that if we integrate these equations. Okay. So, if we integrate these equations by considering y equals to 1, that is P equals to P naught. So, if there is no pressure changes when weight of the catalyst equals to 0, let us say when if there is no, if we do not put any catalyst inside of the catalyst, so then there is no pressure drop. So, then P equal to P naught would be there. Okay. So, then under these conditions if we integrate this equation, so we will get this. So, after that if we rearrange the equations, so we will get y equals to P by P naught equals to 1 minus alpha W to the power half. So, this is the changes of pressure, means pressure, this is the ratio of pressure and weight of the catalyst, W is the weight of the catalyst inside of the bed. So, if we change the accordingly, means if we increase, let us say here if we put 1 kg of catalyst at the beginning. So, then accordingly if we know the alpha value, then what would be the pressures, the other points. So, then that we can find out using this equation. Similarly, if we increase the W, weight of the catalyst gradually increase. So, then accordingly the pressures inside of the bed of the reactors along the length, that will gradually decrease. So, it means the pressure drop will gradually increase. Okay. So, then the equations we can write this. Okay. So, now if we this equations already y equals to this equation we have derived. So, now we have the dx by dw, these equations we have also derived from the design equation dx by dw equals to this. So, here if we put this equation already you have derived and by integration. So, now if we put this here, pressure drop is there. So, P by P naught is there. So, if we put these equations here, so then at isothermal conditions E equals to 0. Okay. So, if you put it 0, so then it would be 0 this part. So, then these equations we can solve and to find out. So, what would be the, if we change the weight of the catalyst, then so what would be the conversions. Okay. So, in since this is the bed of the catalyst. So, if this is the let us say this is the bed of the catalyst. So, along the downs of the reactors we are increasing the weight of the catalyst. So, then if we let us say 1 kg of catalyst, 2 kg catalyst, 3 kg of catalyst, if we gradually increase the amount of the catalyst along the length of that catalyst, so then total amount of the catalyst weight will increase. Therefore, the conversions also accordingly will change inside of the reactor. So, these equations if we solve, means this is the differential equations if we solve by putting all parameters. So, then we will get this table. So, if we plot these tables, x axis W and y axis x, that is the conversion changes. So, it would give a nature of the curves. Okay. So, that I will discuss in the next slide. So, this easily we can solve this type of design equations and these differential equations for a particular packed bed reactor. So, then see if we put want to get a desired conversion. So, then how much amount of the catalyst that you have to place inside of the packed bed reactor, that usually we can calculate. Okay. So, using these equations. So, now the equations what we have derived. So, here dx by dw in terms of catalyst weight that we have derived. So, now here along the length, z is the length of the reactor bed. So, if we want to express that in terms of catalyst length, catalyst bed length or reactor bed length. So, then here we know alpha equals to how alpha and beta, that is the pressure drop factor. So, parameter. So, that is related we know, and this how weight of the catalyst and as a length of the catalyst, length means length of the reactor, that how they are related. So, that these equations we have derived or we have discussed in our previous class. So, just how to means they are interrelated, alpha with beta 0 and W and Z. So, that we know. So, now if we replace this value, means if we multiply alpha with W, so then we will get this. Okay. So, if you multiply alpha with W, so then alpha W will get, and this alpha W we can substitute here. Okay. So, in that equation, these pressure equations we have derived. So, there we can substitute. So, then after substitutions we will get this. So, here in the left hand side you can see P by P naught as a function of Z. Z means that is the length of the packed bed reactor. So, earlier equation was the weight of the catalyst. So, these equations, and so how weight of the catalyst if we change. So, then what would be the pressures at individual points of the reactors, that we know. Similarly, if we change the length of the reactor, so that way also we can express the same equations different form. Okay. So, here also similarly we can get either we can express in terms of pressures along the length. So, here y axis if we put the pressures and x axis that is the z, that is the length of the reactors or bed length. So, then pressures how that would be changes. So, that easily we can find out. Okay. So, now that is the second case. Second case means earlier one, that was if there is, we have assumed that there is no volume changes during reactions, epsilon was 0. Now, epsilon not equals to 0 and temperature not equals to isothermal, not isothermal conditions, temperature may be vary along the length of the reactor. So, if we know individual point temperatures, so then that we have to put in inside of the equations and this part is not 0. So, then accordingly these equations also directly we can solve if we know along the length of the reactor. So, what would be the temperature individual points. So, earlier ones we have assumed that there is no volume changes, fraction volume change was 0 and temperature was isothermals, but these cases if we do not consider there is no volume changes and volume changes may be there, and if the system is not isothermals, in that case this equation directly differential equation we can use and we can solve that. Okay. So, by that way if we solve this equation numerically, so then what would be the pressures and at the same time what would be the variation of the temperatures, what would be the variation of the conversions along the length of the reactors of the packed bed, that easily we can find out using these equations. So, now the effect of pressure drop means pressure drops that is the one parameters in the packed bed reactor. So, if since this is associated with many other parameters, since this is a packed bed reactor. So, here's this is the packing of the catalyst, you know. So, here's if we change the packing of the catalyst or if there is change of the weight of the catalyst or length of the bed. So, with that the pressure drops or pressure changes would be there inside of the reactors. With that if we conduct any reactions, let us say A plus B is going to C plus D, that is the reactant, here product is C plus D. So, that we are getting from here product out. So, if we changes means if there is a changes of the pressure P naught initial pressure to any pressure inside of the bed. So, then how the concentrations of the reactant Ca, let us say this is the initial concentration of component A, final concentration, Ca naught is the initial concentration. So, Ca is the concentration of the reactants along the length, since reactants will be means when reactions will pass through the bed from starting point to the inside of the reactors. So, bed and then it would pass. So, then the concentration of the reactant gradually will change along the length of the reactors or bed. So, therefore, the concentrations how that would vary. So, concentrations that also will change inside of the reactors along the length. So, therefore, the overall rate of the reactions also will change, means once the pressure will change, pressure with that concentration of the reactants along the length of the reactors will change. Therefore, the rate of the reactions will change, conversions will change, volumetric flow rate will change. If we change the W or pressure, if we change the W means weight of the catalyst, and due to the weight of the catalyst the pressure changes would be there, and based on that other parameters also will affect, will change inside of the reactors. So, now we will see means how means let us say if here we have in the left hand side you can see we have considered this is there is no changes of volume, there is no fractional changes of volumes. If we plot y axis P and x axis W we are plotting. Okay. So, weight of the catalyst inside of bed. So, initially W equals to 0. So, then there is no catalyst inside of the bed. So, then what would happen? So, then there is the initial pressure, final pressures would be the same. So, inside of the reactors anywhere there is no changes of pressures or no pressure drops is there. So, then it would be here. So, once we changes the weight of the catalyst, so then the pressure inside of the bed gradually decrease. So, pressures gradually decrease inside of the bed and the pressure drops overall that is increased. Okay. So, pressures gradually decrease and pressure drop increase, increasing the catalyst weight of the catalyst or packed bed reactors. Okay. So, similarly how the concentrations will change. So, let us say along the x axis we are plotting the weight of the catalyst, y axis we are putting concentration of the reactant A. So, if there is no pressure drop means we have designed the reactor such a way that there is no changes of the pressure drop inside of the reactor. So, then the concentrations along the length will follow this, and if there is any pressure drop inside of the reactors, that would be follow these lines. Okay. So, there is pressure drop, considering pressure drop inside of the bed, and if there is no changes of the pressure drops, then that is expected actually. Okay. So, similarly the rate of the reactions, if we plots, if we find out for this particular reactions rate of the reactions, if you are able to know. So, then along the changes of the weight of the catalyst, how the rate of the reactions will change. Let us say this is the second order reactions we have considered. So, then if there is no pressure drop, then it would follow these lines, and if there is pressure drop, so then the rate of the reactions will change accordingly. Okay. Similarly, the conversions also, that already have discussed, if we change the along the length of the reactors, the if there is no pressure drop, then conversions will be high, and if there is pressure drop, then conversions will drop. So, therefore, means whenever we are going to design any reactor, packed bed reactors, so always our objective should be that by putting the same amount of the catalyst, always we expect high conversions of the for that particular reactions, means high yield, high selectivity, high conversion. So, therefore, see here, if there is no pressure drop, that is our expected. Okay. So, but when we are going to design a packed bed reactors, we have to put catalyst inside of the bed, inside of the reactors, and catalyst bed would be there. Once catalyst bed is there, so then there would be a pressure drop. So, once pressure drop is there, so as a result what would happen, the conversions will drop, means as expected. So, that would be down. Similarly, volumetric flow rates of the reactors also, means we means if there is pressure, no pressure drops. So, then we expect that along the length or weight of the catalyst, the volumetric flow rates that remain constant, means throughout the reactors there is no changes of volumetric flow rate, means reactants means the unit of volumetric flow rate is dmq per second. So, volumetric flow rate remain the constant, means throughout the bed or throughout the reactors. So, but in actual case, when there is a pressure drop is there, so then so what would happen. So, along the weight or increasing the weight of the catalyst or along the length of the bed of the particular packed bed reactor, so that a volumetric flow rate gradually will increase. Okay. So, that would affect overall means performance of the reactors. So, here you can see, though means there are so many 5 parameters we have plotted along the weight of the catalyst. So, first one is the pressure, concentrations, rate, conversions, and volumetric flow rates. So, in the ideal case, means so the if our design for that particular packed bed reactor is perfect, so then so what would expect, means ideally we expect that there is no pressure drop in the system, such a way we have designed that packed bed reactors and placed the catalyst such a way that no pressure drop is there, no pressure drop is there. So, if no pressure drop is there, the rate of reactions will be high. If no pressure drop is there inside of the bed, so then conversions will be very good means higher conversions will get. If there is no pressure drop, so then concentration along the length of the catalyst, that would be higher concentrations of that particular reactants will be available inside of the beds, individual points that would come in contact with the catalyst, and that would take part in the reaction, then that would be converted into the corresponding or desired product. Similarly, this is the pressure. So, this is the ideal cases are expected, but in real case there is what is happened, there is some pressure drop is there. So, that is the if there is pressure drop, so then of course, everything will affect, means conversions will affect, rate will affect, concentration of the reactants inside of the bed will affect. Therefore, overall system performance will drop or system performance will be affected. So, these are conversions rate will not get for a particular reaction. So, whenever we are going to design a particular reactor, so always we should expect that there is no pressure drops, or we have to design site such a way that reactors, means I have said that this is let us say packing. So, here let us say reactant A and B that is passing through this inside, this is the inlet, and here product we are getting. So, here we have to place the catalyst in such a way that means there is no pressure drop is developed inside of the bed. So, as if so we can means reactants may come in contact with that catalyst particles or active site, and converted directly into the product. So, here means catalyst if we place randomly over there. So, then means some channel means void spaces would be there, through that catalyst may be a reactant may be passed without taking part in the reaction, that also we have to keep in mind. So, when we are going to design a packed bed, so such a way that so there is no channeling or bypassing of the reactant should be there, at the same times there would not be any pressure drop also. So, means that pressure drop depends on various number of other parameters or factors also, that we will discuss in our next class, means how we can design the packing or packed bed reactors the catalyst bed. So, such a way means here the particle size means is very important also, means here the catalyst we have taken. So, it has particular diameter. So, its diameter may be we can place smaller diameter particles, means this is also catalyst, this is also catalyst. So, but the particle diameter is smaller, this is dp2 dp1 let us say. So, particle diameter means smaller diameter particle we can, the same catalyst is there in both cases, but catalyst particle diameter is different, one is dp1, another one is the dp2. So, either way we can design the particles, means a particular shape, that may be spherical shape. So, it may be smaller diameter, larger diameter. So, that also would affect packing inside of that packed bed reactor. So, based on that also means reactions whatever we are considering, that would affect, at the same time the pressure drop also will affect. So, means reactions we have to conduct inside of the reactor, but we have to design such a way that we can eliminate the pressure drop 0 or close to 0, we can, means 0 is not possible, but close to 0 we can develop, means then if pressure drop is 0 or close to 0. So, that also depends on the catalyst particles we are placing, how we are arranging, how we are placing over there, that part we will discuss in our next class. Okay. So, in our next class we will discuss how the catalyst particles will affect overall rate of the reactions, means conversions, means if we change different size of particles. So, how that would affect overall rate or conversions, means kinetics, these are the things we will discuss in our next class. Okay. Thank you.